Hello everybody, and welcome back. This is going to be Section 3, Part 2. So, this is not exactly the slide that we had left off on, but something important here that I failed to mention. So we have our moon here during the springtide, moon, sun, earth, all in alignment. Right? We draw a straight line here between them. And because the sun and the moon are combining to pull on the entire earth, we have more pronounced tides. Here is the neap tide, have the moon pulling one way and the sun pulling a different way, so we have a little bit less pronounced tides. And the arrows here are actually a little bit confusing. Uh, the bigger arrow should be towards the moon. The moon pulls harder than the sun. I don't know why that's there. Anyway, if we have the moon at this position, right, these are in alignment, but what if we have the moon over here, right, on the opposite side? Is it still going to be a spring tide? Yes. So if we have the moon all the way on the other side of the Earth here, it is still going to be a springtide. You might think that with the sun on one side and the moon on the other, that they would somehow cancel out. This is not the case. It's still going to pull the Earth out, stretch it in that direction, and lead to increased tides. Now, the final thing. Where is the new moon and where is the full moon in this orbit? Right? Which one is which? Okay, so the full moon means it is getting a bunch of sunlight, which is visible to us on Earth. It's going to be here, right? The sun hits this side of the moon, and we get full sunlight here on Earth. This is going to be the new moon over here, right? All the sunlight is hitting this side, and people on Earth don't get to see that. So this would be the new moon here. This would be the full moon over here. Now, I'm going to pause for just a minute. Stay with me. Okay, pause is over. Thanks for staying with me here. So I wanted to include this little bit here. Mont Saint Michael, forgive the pronunciation here. In northern France, you have this little island. People here noticed there was a little island, kind of a nice circular shape, and they built a cathedral on it, a bunch of houses. So this is it at low tide here. You can actually walk over, drive over, whatever. And this is what the island looks like during high tide over here. Do not try to walk over, that is my recommendation. Don't try to drive over either. This is a pretty nice place. I just wanted to put this in as an example, a cool place that was sort of built around tides. It's also, catch me in 20 years living in one of these houses. All right. So we're going to move on from tides now and talk about waves. All right. So we all love, heard of, waves are generated by offshore winds blowing on the water. Friction as it blows on the water, and it causes the water to move. Sometimes these winds can be thousands of miles away from the actual shoreline and drive the water all the way the distance over there. Right? This is transferring energy to the water, which then transfers energy to the coastline and helps to shape it. Now, the energy of the wave is about proportional to the square of the wave height. So, as an example, we have a 1 foot wave, give that 1 unit of energy. A 2 foot wave is going to have 4 times as much energy, and a 3 foot wave is going to have 9 times as much energy. The point here being that you need much more energy just to produce a little bit bigger of a wave. Right? So, we have all these things on tsunamis where you see the really big wave. It's not just 30 times more energy in a 30-foot wave than a 1 foot one. It's going to be 900 times more energy in the 30-foot wave compared to a 1 foot wave. Yeah. Now, these help to shape coastlines, create all sorts of coastal landforms, which we'll talk about more in the next section. This is different depending on whether you have an active or passive margin, as we talked about. And finally, these help to transport sand and sediment for long distance, part of this sediment deposition system. Now, if we look in more detail, we have our waves coming out from deep ocean here, getting closer to the shore. They tend to slow down as things get shallower, and as the waves slow down, the waves in back are comparatively moving faster, right? And once we get here in the surf zone, the back of the wave is moving so much faster than the front that it actually launches over and crash, and the wave gets too high, gets unstable, and it just breaks. And this is what causes the surf to come up and the waves to break here. I'm not going to spend too much time on that. One thing you should know, right, is the coastline really has different patterns depending on where you are geometrically, right? So we have this headland here poking out into the sea, right? This is going to get a lot of wave action in the form of erosion, right? High wave energy and erosion. See these waves sort of diffract here. Don't worry about getting too technical with it, right? Full lines here, but this is sticking out, right? So a lot of the waves actually curve inward to hit it. They don't necessarily move in straight lines, right? A lot of waves hitting at high energy and actually erode the coastline over time. As opposed to these other areas, the bays, which are the opposite, kind of protected, kind of inland here, right? You see the waves actually prefer to avoid it geometrically. So this is actually going to be a case of low wave energy and deposition, and down at the beach for these. So final section will be on coastal landforms. Stick around, don't go anywhere, I'll see you then.